Think about an egg. We just see the shell, but do we know what's inside it? How do you know? You've probably seen an egg before, and you've probably gotten a chance to break one open, and so you probably know what it looks like inside. This direct knowledge is what we call evidence in science. So what about the Earth? What is inside the Earth? This is a little tougher in that most of us don't really have a lot of direct evidence. Have you ever dug a hole? How far down did you get? No matter how deep the hole was, you probably only ran into soil and rock. So really, based on direct evidence, we might have the idea that the Earth is made up of solid rock. So we're going to start with this theory. You have two pieces of paper that have two quarter circles on them. Tape them together as indicated on the paper. It should look like this. And now this half circle is going to be our model of the Earth. You also have a record section of 17 different seismic stations that recorded the 2010 Haiti earthquake. Look down along the bottom of the record section. The x-axis shows us the location of each seismic station in degrees, which you may be a bit confused about. What do you mean when we say the distance of the seismic station from an earthquake is given in degrees? The degrees represent the geocentric angle of each station in relation to the earthquake. Remember, the Earth is a sphere, so it can be tricky to try to describe the distance between objects on its surface, especially when you have 17 of them, and they may or may not be lined up in a nice straight line. So on our model, we have the center of the Earth down at the bottom, and the curved part represents the surface of the Earth. The earthquake occurs at 0 degrees down in the bottom right of the circle. Say one station is listed as having a geocentric angle of 145 degrees away from the earthquake. We can take a protractor and line up the little dot in the middle with the middle of the Earth on the model. Make sure the horizontal lines are lined up with the bottom lines of our model. Start with the earthquake at the 0 degree mark and follow the protractor around to the 145 degree mark. This is the location on Earth of the seismic station with a geocentric angle of 145 degrees in relation to the earthquake. Now look at your record section. The triangles at the top represent a seismic station. Label them 1 through 17. For each one, follow the middle line down to the x-axis and estimate the geocentric angle of the station. So we're going to use a protractor to locate the correct angle on the Earth model. The first station is about 1 degree distance from the epicenter of the earthquake. So we're going to line up our protractor with the center of the Earth, and we're going to measure 1 degree up. Make a little mark at that 1 degree line. Draw a light line from the center of the Earth to the surface of the Earth. Label this point as station 1 and write the degrees you measured. Then repeat this for the other 16 stations. When you're done, it will look something like this. So our earthquake down there at 0 degrees radiates energy out in all directions. The energy is picked up by each station at the surface of the Earth and recorded. Now that we have a location of 17 seismic stations on the surface of the Earth, we want to determine each station's linear distance away from the earthquake. This will tell us the actual distance through the Earth that the seismic waves traveled. With a new color pencil, draw a line from the epicenter of the earthquake to each seismic station we have plotted. So for station 1, use a ruler to draw a straight line from the earthquake to the location on the surface where station 1 is plotted. Repeat this for the next station, and then the next, and until you have drawn a line for each station. Then use your ruler to measure the length of each of these lines in centimeters. You have a Google Sheet in Classroom. Add the station distance in degrees and the length of each line into the appropriate columns.